All right, we are given a sample of a gas that has a mass of 0.100 grams. We're given its pressure, which is 70.5 millimeters of mercury. We're given its volume, because it's contained in a 256 milliliter flask. We're given its temperature at 23 degrees Celsius. We're asked to find the molar mass of the gas. Well, the molar mass of the gas is going to be how many grams are contained in a mole, or the grams per mole. We know the grams, we got to find the moles. If we recall that we know the gas constant, 0.0821 liter atmosphere per mole per Kelvin, we recognize that we have P, V, R, and T, and all we need is N. So the equation we're going to use to find out N is PV equals nRT. We have P, we have V, we have R, we have T, we have everything we need to find N. So to find N, we'll have to, divide both sides by RT, both sides of the ideal gas law, and we get our equation. N is PV over RT. That's the equation we're going to use to find the moles in our sample. Now, before we plug everything into this equation, I'm going to check to make sure my units match. I'll be using this gas constant, and I'll recognize that the pressure units that I have are millimeters of mercury, but I need to convert that to atmosphere. So there's going to need to be a conversion done there. I'll also notice that my volume units are in milliliters, but I need them in liters. And of course, we're using the gas law, so we're going to need to convert degrees Celsius into kelvins. So we'll start with our pressure, 70.5 millimeters of mercury. We're going to convert my millimeters of mercury into atmospheres. How many millimeters of mercury are in an atmosphere? 760. Millimeters of mercury on the numerator and denominator cancel. And so I will take 70.5 and divide that by 760 and get 0.0928 atmospheres. The volume transition, that should be easy, right? There's 1,000 mils in a liter, so we're going to need to divide this by 1,000 to get to 0.256 liters. This is easy as well. We're just going to go ahead and add 273 here. And that's going to give us 296 Kelvin. Okay, now we're ready to plug everything in. So let's do this. The number of moles is going to be PV over RT, where pressure is 0.0928 atmospheres. Our volume is going to be 0.256 liters. We'll divide that by 0.0821, or R, liter atmosphere for every mole, for every Kelvin. And then we'll also need to divide by 296 Kelvin. Let's see, on the denominator, Kelvin cancels inverse Kelvin. An atmosphere on the numerator cancels an atmosphere on the denominator. And the same happens with liters, one on the numerator, one on the denominator. The only unit we're left with is an inverse mole on the denominator, which is a mole, which is good because that's what I'm looking for. Now it's just time to do the multiplication and division. So let's see. 0.0928 times 0.256 divide by 0.0821, and we're also going to divide by 296. 0.0009 0.0978 moles. So I got my grams, 0.1 gram. We're going to divide by my moles. Let's see. 0.1 gram divide by 0.000978 moles. That'll give me my molar mass. 0.1, divide that by 0.000978. 102 grams per mole. Now, our problem goes on further to state that the empirical formula of the gas, which is the lowest whole number ratio of the atoms in the gas, in the molecule of the gas, is CHF2. If this is the empirical formula and this is the molar mass, what's the molecular formula? Well, to figure this out, I'm first going to find what is the, so to speak, molecular mass of this empirical formula. I've got a carbon. I've got one of those times 12 grams per mole. I've got a hydrogen, one of those times 1 gram per mole. And I've got 2 fluorines times 19 grams per mole. That's 38. Add those up. That's 51 grams per mole. These don't match. But you recognize multiplying this by 2 gives me this. So I need to multiply my empirical formula by 2 to get my molecule. So let's see, if I multiply this by 2, I'm going to have 2 carbons. I'm going to have 2 hydrogens. I'm going to have 4 fluorines. And this is going to be your molecular formula of the gas sample.